So quickly, we were everyone able to hear me, right?
Right.
Able to hear me?
Yes, sir. Yes, sir.
Okay. So able to hear me, right? So last class we were talking about transients, right? We were seeing about first order and second, sorry, first order transients, source free RL and source free RC circuits, step response of an RC circuit and step response of an RL circuit. So what was the only four formulas for the entire transients. Only four formulas for the entire transients, or rather the first order circuits for RC circuits, source free RC circuits. Source free RC circuit. Tell me what is the formula for source free RC? V of t is equal to V naught e power minus t by tau. What is tau? Tau is equal to RC for RL, source free RL circuit. I of t is equal to I naught e power minus t by tau. And what is tau? Tau is equal to
L by R.
L by R. Okay. So, and again, step response of an RC circuit and RL. RC circuit, what is V of t? V of t is equal to V of infinity plus V of 0 minus V of infinity e power minus t by tau, and tau is equal to RC. RL circuit, I of t is equal to I of infinity plus I of 0 minus I of infinity e power minus t by tau. Tau is equal to L by R. Okay. So what do you call this part of the response? This is called as the transient part, and this is the steady state part. Transient part, steady state part. Steady state and the transient part. Why is it called as transient? Because it dies at t is equal to infinity. This part will become 0. That is why it is called as transient. Okay. And what else you have? Transient response, steady state response. What is forced response and natural response? What is forced response and natural response? So V of t can also be written as V of 0 e power minus t by tau plus V of infinity into 1 minus e power minus t by tau. So in this is called as, what response is this?
Natural.
What response is this? This is called as
Natural.
natural response, and this is, the other one is called as forced response. Is this clear? This is I wrote the same equation in a different way. Okay, this is also equal to this one.
Clear.
I'm sorry.
No, clear.
Clear, right?
Right.
Okay, why do you call it natural response and forced response? Because this is due to the stored energy in LNC elements, and this is due to the external source. V of S is nothing but this is because of the external source. That is why this is called as forced response, and this is natural response, steady state response, and transient response. Four equations. Okay. So try to solve this. Determine V of t for t greater than 0 and its value at t equal to 1 second as well as at 4 seconds. Try to do this. And you have a switch. What is the condition for the switch? Condition for the switch?
Right now, After 0 plus, it will be turned to position B.
Yes, at t equal to 0, the switch is moved from position A to B. Okay, so so this comes under because even after the switching action, there is a voltage source, right? So again, so what is the equation? It's an RC circuit. V of t is equal to V of infinity plus V of 0 minus V of infinity into e power minus t by tau. 3 steps. Find V of 0, find V of infinity, find tau. 3
Right.
steps. 1, 2, and 3.
I
Find V
think
of 0.
I
V
think
of
V
0
of
is nothing
0
but
is 15 volt.
V of 0 is equal to V of 0 minus is equal to V of 0 plus. So at t is equal to 0 minus, you have a steady state condition, right? Steady
Right.
state condition. T equal to 0 minus is a steady state condition. And what else is a steady state condition? Plus infinity, right?
Plus
0
infinity, yes.
minus and plus infinity, both are steady state conditions. At t equal to 0 minus, what is happening with the circuit? The switch is at position A. This is what you call the source is not connected, only this source is connected. So 24 volts is connected to this is how the circuit is. And at steady state for DC, what does capacitor act? Open circuit.
Open circuit.
Yeah, will be my V of 0, 3 and 5. So what is V of 0? 24 into 5 by 8,
15.
15 volts. Okay. To find tau, you should consider just after switching T of 0 plus condition. Okay, after switching or T greater than 0 condition rather, you can say T greater than 0 condition. T greater than 0 condition, what is the position of switch? It is at position B, right? Position
Right.
B, what is R equivalent? 4 kilo ohms. 4 and C is 0.5 milli, right? So RC will be tau is equal to RC, which is equal to 4 into 0.5, 2 seconds. Okay. Next, what else we need to find? V of infinity. V of infinity, as I told you, it's also a steady state when at t is equal to infinity. T is equal to infinity. As t tends to infinity, what happens to the circuit? The switch is at position B and this part will be left. This part will be left. 4 kilo ohms. And again, the capacitor will act as an open circuit. So V of infinity will be, how much is V of infinity?
30 volts.
30 volts. So V of t is equal to 30 plus 30 plus 15 minus 30 e power minus 0.5 t. Okay, so this will be 30 minus 15 e power minus 0.5 t. So what else I need to find?
At 1 second and
At t is equal to 1 and 4
4.
seconds. T equal to 1 second. Substitute. T is equal to 4 second. Substitute. V of 1. 30 minus 15 e power minus 0.5. And V of 4 is equal to 30 minus 15 e power minus 0.5 by 5 into 4 is 2. Okay. Clear, right?
Right.
Next, try to find this. Determine V of t for t greater than 0 and its value at 0.5 seconds. 3 steps. Find V of 0, V tau, and then infinity. tau and V at infinity. 3 steps. Try to do it. So what is V of 0? So what is the switching position?
Well,
Switch is closed at t equal to 0. The switch is closed at t is equal to 0. That means at t equal to 0 minus the switch is open. Okay, and the switch is open. Only this part is a circuit. So is 10 volts. V of 0 is directly 10 volts. Right?
right.
Tau. After switch is closed, after the switching action. After the switching action, both the sources are there. Okay, and I need to find the equivalent resistance. R equivalent. What will be R equivalent as seen from this? How to find it? R Thevenin. Turn off
12 by
all
8.
the voltage sources. Yes, 2 and 6 are in parallel. 2 parallel with 6 to
12
12
by
by
8.
3. 4 by, sorry, 3 by 2. Okay, C equivalent is again 1 by 3. So tau is equal to R equivalent into C equivalent, which is 3 by 2 into 1 by 3, which is 1 by 2 seconds. Okay, and V of infinity at t is equal to infinity. Both the sources will be there, and it's a steady state condition, which is a steady state condition. So what happens under steady state? The capacitor will act as an open circuit. I have to find the voltage across it. Both the sources are acting. How to find it?
Nodal.
Hmm? Yeah, you can do nodal, mesh, whatever you want. Find the value. Find the voltage V here. V minus 10 by 2 plus, I'll do it here. V minus 10 by 2 plus V plus 5 by 6 is equal to 0. Okay, V by 2 plus V by 6 is equal to 10 by 2 is 5 minus 5 by 6. Okay, V is equal to 25 by 6 into 6 by 4. Okay, 25 by 4 volts. Okay, V of infinity is 25 by 4 volts. So V of t is equal to 25 by 4 plus what is V of 0? 10 minus time again 25 by 4 into e power minus 2t. Okay,
Right.
clear?
Clear.
You can find its value at t equal to 0.5 seconds by substituting t is equal to 0.5. What happened? You're saying something?
No, nothing.
Oh. Next, determine I of t for t greater than 0. Determine I of t for t greater than 0. Three steps. I of 0, it's an RL circuit, right? I of 0, tau, and I of infinity.
I of 0 is 2.
I of 0 is
2.
okay. See what is the switching action that's happening here?
First, I mean,
At t is equal to 0, the switch
it's
is
open.
getting opened. So before the switching action, that means t equal to 0 minus, what's happening? The switch is in a closed position. That means the 3 ohm resistor is getting bypassed. Okay, and t equal to 0 minus is a steady state condition. So under steady state, my inductance acts as a short circuit. So I of 0 minus or I of 0 is equal to 10 by 2, which is 5 amperes. Okay, find tau at t greater than 0 after the switching action. That this is opened now, the switch is opened, resistor comes into action, t equal to 0 plus. Now, as seen from these terminals, find R Thevenin. Short this 3 plus 2. R Thevenin or R equivalent is 5 ohms. L equivalent is 1 by 3. So tau is equal to L by R equivalent 1 by 15 seconds. Right? And then I of infinity.
Sir, have you written anything?
What happened?
Okay. Right now, I got the slide updated.
Okay. Okay, I of infinity is equal to at t is equal to infinity. Again, this is a short circuit. Both are there. So I of infinity is 10 by 5, 2 amperes. Right? So I of t will become I of infinity 2 plus 5 minus 2 e power minus 15t. So 2 plus 3 e power minus 15t. Okay, this is I of t. Clear?
Okay, please.
Again, define I of t for t greater than 0. Simple questions. If you know the problem and the concept, or if you know the formula and the concept, it's a one-step questions. All are one-step questions. The whole of transients is with the four formulas I told you. Only the four formulas. If you are thorough with the four formulas and the concepts behind those, you are through with the transients. Okay? As simple as that. If you are okay with those four formulas and the concepts of transients, you will be through with transients. Okay. So again, what is I of 0? I
9
of
amperes.
0 is before the switching operation. So before the switching operation, what is the position of switch? The switch is opened at t equals 0. That means it was closed before. Okay, it is closed before. Okay, it was closed before. That means it's a short circuit, complete short circuit. So I of 0 is 9 amperes. Whole of this current will flow through this. Okay, 9 amperes. Okay. And I tau is equal to after the switching action. After the switching action, the switch is opened. So as seen from these terminals, I need to find the R equivalent. This will be opened. So 5 and 10 are in series. So R equivalent is 15 ohms. L equivalent is 1.5 Henry. So tau is equal to 1.5 by 15, that is 0.1. Okay. Then I of infinity directly. I of infinity after the switching action. That means the switch is opened. So this comes into action. So 9 amps gets divided between 5 ohms and 10 ohms. Again a steady state. So this will become 9 into 10 opposite resistance by total resistance. 3 fives, 3 threes, sorry, 3 fives, 3 threes, 5 twos. It is 6 amperes. So I of t is equal to 6 plus 9 minus 6 e power minus 10t, or 6 plus 3 e power minus 10t. Okay.
Right.
Try to solve this one. It's a gate question, a 1 mark question. It's a direct question. Try to solve this one. In the figure shown, the capacitor is initially uncharged. Which one of the following expressions describes the current I of t in milliamperes for t greater than 0? I of t for t greater than 0. So this is an RC circuit and it is initially uncharged. That means V of 0 is given as 0. So find tau. Tau is equal to, as seen from these terminals, this is shorted. So these two are in parallel. 2 by 3 into 1 is 2 by 3 seconds or 2 by 3 milliseconds. Why? This is kilo ohms and this is microfarads.
Micro.
So it will be 2 by 3 milliseconds. Option A, correct. Okay. So V of infinity. What is V of infinity? V of infinity will be, as seen from these terminals, it's a steady state. So 5 volts gets divided. 5 into 2 by 3. It is 10 by 3. Okay. 5 into 2 by 3, 10 by 3 volts. So V of t is V of infinity 10 by 3 plus 0 minus 10 by 3 e power minus t by tau. Let it be. Okay. So 10 by 3 into 1 minus e power minus t by tau. So this is V of t. And how to find I of t? So I of t is, this is the voltage V. So V by 2K, that is V of t by 2 milliamperes. So this will be 5 by 3, 1 minus e power minus t by tau. Okay. Tau is 2 by 3 milliseconds. And this is milliamperes. So option A. Okay.
Okay.
Okay. Again, a numerical question. Try to solve this. In the circuit shown in the figure, initially the capacitor is uncharged. The switch as is closed at t equal to 0. 2 milliseconds after the switch is closed, the current through the capacitor in milliamperes is. So initially uncharged directly. V of 0 is 0. So V of t will be directly V of infinity. Only the forced response. 1 minus e power minus t by tau. And what is tau equal to? As seen from these terminals, after the switch is closed, these two are in parallel. 1 into 4 will be 4 milliseconds. Okay.
Right.
Tau, we got tau. Next, V of infinity. V of infinity will be 5 will equally get divided. So it will be 2.5 volts. So V of t will be 2.5 into 1 minus e power minus t by 4 milliseconds. T is given as 2 milliseconds. So V of 2 milli will be 2.5, 1 minus e power minus 2.
Half.
This will be 1 by 2. Yeah, 0.5. So how much did you get it? 1.516. Okay. Okay.
Okay.
So all these are kilo ohms, right? So this will be milli and this is also milliamp. See, one thing we have drawn the graphs for source-free RL and RC circuits. I just want to draw this, what do you call, for source, with the source RC and RL circuit or step response. What is V of t? I missed that. V of infinity plus V of 0 minus V of infinity e power minus t by tau. So how will it look? Initially, this is V of 0, exponentially decaying term, and this is V of infinity. Right? At t is equal to infinity, what happens? The voltage, the transients will die out, and the voltage will be constant at V of infinity. Okay? This is the circuit or the diagram. Similar for current, exponentially decaying I of t. This is I naught or I of 0, and this is I of infinity. Okay, clear, right? At t equal to infinity, what happens? This term will be 0, only this will remain, V of infinity. At t is equal to 0, or t is equal to 0, what happens? Only this part will come. Okay, t is equal to 0, e power minus 0 is 1. So V of minus V of infinity and plus V of infinity get cancelled. Only this will be there. So V of 0, it starts at V of 0. At infinity, it will be V of infinity. Okay, clear?
Sir, for current, the at steady state it will reach up to 0 now.
This is for RL and this is for RC.
Okay, okay.
Okay, RL
Yes.
circuit also it will reach a time of infinity. See, whenever in transients we talk about currents, it's about RL circuits. In case of voltages, it's about capacitive circuits. It's generalized. If for any problem, if I want the current through the capacitor, that's a different thing. Generally, when we talk about currents, it's about RL circuits. When we talk about voltages, it's about RC circuits. Okay, clear?
Clear.
Yeah.
It's a good problem, but it takes a bit of time. If you can try it, if you want to try it, take a screenshot of this and try to solve this. Okay, try to solve this. It's a good one. You can draw the graph after drawing this. You'll get a lot of insight on this. Okay, take a screenshot of it. Yeah. Okay, now coming to the second order circuits. Okay, second order circuits. So second order circuits, you'll only need the concepts, okay, rather than solving problems. Solving problems takes time. I'll also give you some shortcuts to do the second order circuits in what you call competitive exams. Okay. Okay. Rather than going with doing more problems from second order circuits, let's get into the concepts. See, for a capacitive circuit, what we have seen, V of t, or sorry, I of t is equal to C dV of t by dt, right? At t is equal to 0, what happens? At t is equal to 0, I will be in infinity. I will be infinity. I will tend to go infinity at t is equal to 0. Okay. So, or t is equal to 0 minus, let me say t equal to 0 minus, what happens when we have seen t is equal to 0 minus is a steady state condition. Steady state condition, right? What else is a steady state condition? Plus infinity is also a steady state condition. These two are steady state conditions. That means the switch, we will assume that the switch is closed or the switching operation took place at t equal to 0. It's in the initial position from t equal to minus infinity to 0 minus, and 0 plus to plus infinity. Again, the switch after the switching action, 0 plus is a transient condition and plus infinity is a steady state condition. So what happens is V of 0 minus whatever the voltage at just before the switching operation will be same after the switching operation, right? The capacitor does not allow sudden changes. Capacitor does not allow sudden changes in the voltage across it, right? Capacitor does not allow sudden changes in the voltage across it. That means instantaneous voltage will always be or at t 0 minus and 0 plus, the voltage will be same. That means even if you remove the source, even if the source is removed, what happens? The voltage will be same. Okay. So for example, this is my capacitive circuit, plus minus. So at t is equal to the 0, the switch is opened. Okay, this is voltage. What happens now? The capacitor initially it's getting charged this way. Okay, and it gets charged to the full voltage V. After the switching operation, what happens? Initially it is getting charged this way. After the switching operation, what happens? T equal to 0 plus, the voltage will be same, right? V of 0 minus will be same as V of 0 plus. But what happens? The current direction gets reversed because whatever the energy stored will have to be dissipated to the resistor. Okay, and to have the same polarity of voltage, the current gets reversed. Remember this. For a capacitor, the current gets reversed at t equal to after the switching operation. Okay. Understood this? So also what happens is this voltage capacitor acts as a voltage source. At t equal to 0, capacitor acts as a voltage source. Okay, capacitor acts as a voltage source, or the capacitor can be replaced by a voltage source. Can be replaced by voltage source. Only for t equal to 0 plus. Okay, not always. At t equal to 0 plus can be replaced by a voltage source. Okay, the capacitor can be replaced by a voltage source. Okay, of value V of 0. Of value V of 0 or V of 0 minus, which is same as V of 0 plus. Okay, this is for capacitor. Similarly, for an inductor, what is the current equation or voltage equation? V of t is equal to L di by dt. So it again opposes sudden changes in current across it. That means I of 0 minus is equal to I of 0 plus, which is equal to I of 0. Okay, so At t is equal to 0 plus, it acts as a it acts as a current source, and what happens? Voltage reversal happens. Current source and voltage reversal happens. Voltage reversal happens. Here what happens? It acts as a voltage source and current reversal happens. Current reversal happens. Okay, understood this? In case of a capacitor, what happens? In case of capacitor, at t equal to 0 plus, it acts as a voltage source and current reversal happens. In case of inductor, it acts as a current source and voltage reversal happens. Okay, so I of 0 minus is equal to I of 0 plus is equal to I of 0 in an inductor. That means the just before the switching action, just after the switching action, the current through the inductor will be same. Similar to this, the current through the inductor assume this is a current source. So this is I in this direction. What happens now? Previously the voltage is like this, right? Before the switching action. After the switching action, it acts as a current source and this will become positive and negative, right? After this was asked in the first class of transients. I don't remember who asked it. The current is going, the current will continue to flow in this direction only, and the polarity of the voltage across the inductor gets reversed. Similarly, the voltage polarity will be same in case of capacitor, but the current direction gets reversed in case of a capacitor. And in case of an inductor, the current reversal happens. Sorry, voltage reversal happens in inductor. Current reversal happens in case of capacitor. Clear? Clear, right?
Clear, clear.
Okay. You see, sometimes these type of questions you may get in these problems from second order circuit. If you remember what is a second order circuit, you need to have two inseparable L and C elements, right? Inseparable L and C elements. There is one L and one C element, so which are separate. So what happens? This is an second order circuit. You need second order differential equations to solve this. Okay, you need second order differential equation to solve this. Okay, what is the general equation for an RLC series circuit? If you see, if I write the what you call KVL in this loop, minus 10 is equal to, sorry, minus 10 plus I into 10, 10 into I of t plus what is the current through the inductor? 1 by L integral V of t dt. Sorry, voltage across the inductor. Voltage across the inductor, I'm sorry. It's an KVL, right? L di by dt. 1 L di of ty dt plus what is the current through the, sorry, voltage across the capacitor in 1 by C integral I of t dt is equal to 0. So this is the equation for this, or I can write it as something like is equal to 10. Okay, this is the generalized equation. So at t is equal to 0, so before what happens, the switching action at t equal to 0, the switch is getting closed. Initially, everything is uncharged, right? The inductor is not charged, the capacitor is not charged. Okay, so after the switch, just after the switch is closed, t equal to 0 plus, t is equal to 0 plus, what happens? T equal to 0 plus. Okay, I think I have to give you this one more theory. Just a minute. Sorry. So voltage current through the capacitor I of t is equal to C dV by dt. Okay, C dV of t by dt. What happens at t equal to 0 plus, or t is just after the switching close, t equal to 0 plus, or what happens is when dt is 0, I will be infinity. So I of t will be infinity. I of t infinity or maximum current. Okay, when will the maximum current flow? Under short circuit condition, right?
Right.
Okay. Okay, under short circuit condition. Okay, at t equal to 0 plus, I of t will be infinity, that is maximum current. Maximum current happens at short circuit condition. Okay, and t of infinity at t is equal to infinity is a steady state condition. In the steady state condition, what happens? At t is equal to infinity, I will become 0. That means I of t is equal to 0. Minimum current condition, or I of t 0 is an open circuit condition. That, what does this mean? Capacitor acts as open circuit for DC, but the same capacitor t equal to 0 plus just after the switching action acts as a short circuit. Okay. Okay, acts as a short circuit, or it will be replaced by a voltage source whose value is V of 0 minus, because as I told you, it will act as a voltage source just after the switching action. I told you the current reversal happens, but the voltage will be same as t equal to 0 plus. But if it's an uncharged one, the voltage will be 0. Voltage 0 is a short circuit condition, right? So the capacitor will act as a short circuit at t equal to 0 plus, and the same capacitor acts as an open circuit at t is equal to infinity. Is this clear? T equal to 0 plus, capacitor acts as a short circuit, and open circuit at t equal to infinity. Okay?
Okay. Okay.
Sir.
Yes. So for this is for an RC circuit. Now RL circuit. Okay. Again, if I have a switch here, which is closed at t equal to 0. So again, V of t is L di by dt. Okay, at t is equal to 0 plus, what happens? T equal to 0 plus, V of t will be, V of 0 plus will be infinity. That means infinite voltage or maximum voltage. Maximum voltage is an open circuit condition, right? Open circuit condition. Or will be replaced by the current source. If it is charged, it will replace by the current source, and if it is uncharged, it will be replaced by an open circuit at t equal to 0 plus. At t is equal to infinity, V of t will be 0, which is a short circuit condition. Okay, remember this at for DC. Inductor will act as a short circuit at steady state, under steady state. But just after the transient action, it will act as an open circuit when it is uncharged. If it is charged, it will be replaced by a current source of the same value at the time of switching. Okay. T equal to just after that instant, t equal to 0 plus, capacitor acts as a short circuit, inductor acts as an open circuit. Clear?
Clear, clear, sir.
Okay, any doubts in this? The concept is important, that's why I'm repeating. Is this clear?
Clear, sir.
Okay. Yeah, now coming to this, as I gave you this 10 is equal to 10 into I of t plus L into di of t by dt plus 1 by c integral I of t. Okay, so at t is equal to 0 plus, what happens to the capacitor? At t equal to 0 plus, just
Short
we have
circuit.
seen.
Short
Capacitor
circuit.
will be short circuit and inductor will be open circuit. Okay, capacitor will be short circuit and inductor will be open circuit, right?
No current.
Huh? What happened?
No current, right, sir?
Yeah. Okay. So just after the closing time, right? Just after the
Right.
closing time, because inductor is uncharged and capacitor is uncharged. Just after the switch is closed, no current flows through this. Okay, t equal to 0, what I told you, the voltage across the capacitor will be 0. That means it's a short circuit. Voltage across the capacitor is this one. This will tend to be 0. So 10 is equal to 10 into I of 0 plus plus L is 1 Henry. Okay, 1 into di of 0 plus by dt. Okay. Also at t, as you have said, at t equal to 0 plus, current is 0. So that is I of 0 plus is 0. So this will become 10 is equal to di of 0 plus by dt, or di by dt at t is equal to 0 plus is 10 amperes per second. Okay, understood this? What does this mean is, just after the switch is closed, there is no current. Okay, current is 0. I of t is 0 or I of 0 plus is 0. But there is di of di by dt, or rate of change of current is there at 10 amperes per second, as you can see from this. Understood this? There is no
Yes, sir.
current flowing, but there is di by dt. Okay.
Okay, okay.
Now, what else you have to find? D square I by dt square. Is this clear? Di by dt is at t equal to 0 plus is 10 amperes per second. Also, you have to find d square I by dt square at t equal to 0 plus. So, again, bringing this equation here and differentiating it again, you'll get okay. And differentiating again, you will get something like this. Sorry. So 10 differentiation is 0. 10 into di by dt plus L d square I by dt square plus 1 by C I of t. Okay, so this at t is equal to 0 plus, what happens to this? So this is 0 is equal to 10 into what is di of 0 plus by dt? You have it as 10. Okay, plus L is 1 Henry, d square I of 0 plus by dt square plus I of I of t, or I of 0 plus is 0, 0 by c
0.
is 0. So d square I of 0 plus by dt square is nothing but minus 100 ampere square plus second square. Okay. So rate of change of current, and there is also what you call velocity and acceleration of current. This is how you can say. Okay, di by dt at t equal to 0 plus and d square I by dt square at t equal to 0 plus. Okay, you understood the concept behind this. There won't be current at t equal to 0 plus, but there will be change of currents at 0 plus. Okay.
Clear, sir. So why we haven't talked about this, say, like these two cases in the first order circuit?
First order circuit, what case?
like just after closing this at the same instant and the steady state the capacitor value.
Yeah, see, okay, why I'm saying it now and not before? Why I
Yes, yes.
went replace the capacitor with a voltage source before and I'm replacing it now? Because see, what you call first order circuits are very basic circuits. I think, as I told you, I've given you the four formulas, or rather two formulas. With those two formulas, you'll get all the answers. But when coming to the second order circuits and concepts like this, I think you need some more input. The next problems you'll understand that, or why I'm stressing it now, because I don't want
Okay,
to
okay.
give it beforehand. You can do it that way also, but the simpler way is to remember that way. Otherwise, the next concept I want to tell you is using Laplace transform. Second order circuits, basically you'll be solving using Laplace transform techniques. I don't want you to use Laplace transform for first order circuits because first order circuits are very simple. It can be done directly. Okay.
Okay,
So
okay,
now because you need Laplace transform and Laplace transform of all these, that is why I'm giving you the concepts.
okay, okay.
Okay. Yeah. Try to do this. The circuit shown, steady state is reached with the switch open. Okay, at t equal to 0, switch is closed. Determine VA of 0 minus, VA of 0 plus, VB of 0 minus, and VB of 0 plus. Oh, this is a first order circuit. Okay. And if first order circuits, I think you can do it as a homework. Simpler one. You want me to do it now? V of 0 minus VA of 0 plus, VB of 0 minus, and VB of 0 plus. At t equal to 0 minus, what happens? The capacitor will be opened. It's a steady state condition. Steady state condition, t equal to 0 minus. Okay, switch is capacitor is open and the switch is open. Okay, the switch is open. That means no voltage source. This is how the circuit is. Okay, this is how the circuit is. So, okay, this is important. VB of 0 and this is VA of 0. So, what is VB of 0? Minus VA of 0 minus VB of 0 minus is the total voltage, 5 volts
Yes,
directly.
sir.
Okay, and VA of 0 minus is gets the
0
voltage
volt.
actual. Hmm?
The 0
How
volt.
much?
No? So no current flow through 10 ohm and 20 ohm. No?
Okay, no current flows through this.
So
But there will still be voltage division rule.
How, sir?
Oh no, right, right. No current flows through this. The voltage will be V 5 volts. 5 volts should appear. 5 volts, will the 5 volts appear? Yes, the whole voltage will appear across these terminals. Okay. Okay, the whole voltage will appear across this. Okay. Let me think once again. VA of 0 minus. It won't be 0 volts for sure. It won't be 0 volts. Will there be voltage division or not? No voltage division. Correct. 5 volts will appear. Okay. 5 volts should appear because this is an open circuit. Wherever you measure the voltage between these 2 points, here, no voltage drop. Okay, 5 volts will appear. Okay, you can measure between any 2 points, you'll get 5 volts. Okay,
Right.
if I measure between these 2 points or these 2 points, I may get 0, but anything between this and this will definitely be 5 volts. Okay, 5 volts will appear. Think as if you are measuring the voltage, okay, using a multimeter. If you use a multimeter and measure the voltage, you'll get 5 volts. Okay, VA 0 minus. Understood how VA 0 minus?
Yes, sir.
Okay,
Yes, sir.
because it's an open circuit, the voltage will appear across all. It won't be 0 for sure. Okay, and there won't be any voltage division because no current is flowing, no voltage division. Okay, now tell me what is VB of 0 plus quickly. What is VB of 0 plus?
VB, so it will be 5 volt.
How
It
much?
will be 5 volt. 5 volt.
Yes. As I told you, it will be just after the switch is closed, the capacitor will be replaced by a short circuit or a voltage source of value equal to the just before the switching. So the voltage cannot change instantaneously across a capacitor. So VB of 0 plus is solved, right? We solved all this. Now VA of 0 plus just after the switch is closed. Okay, just after the switch is closed, how will the circuit be? Sorry. So this will again be a voltage source. This is VA. 10, 20, 10, 10, 5 volts, and this is 5 volts. Okay, remember the voltage polarities. Now you have to find the VA. Understand, this is the circuit at T is equal to 0 plus. Now find VA. How to find VA? Use nodal analysis. This node voltage is 5, this node voltage is 5. VA minus 5 by 10 plus VA by 10 plus VA minus 5 by 20 is equal to 0. Okay. So VA by 10 plus VA by 10 plus VA by 20 is equal to 5 by 10 is 1 by 2 plus 5 by 20 is 1 by 4. Okay. And let me write it that way only. 5 by 10 plus 5 by 20. So LCM will be 20. This is 2 plus 4 VA plus 1, 5 VA by 20. 5 VA by 20 is equal to 20. 15 by 20. 20, 20 gets cancelled. VA is 3 volts. Or at T equal to 0, VA of 0 plus is 3 volts. Okay, t equal to 0 plus VA of 0 plus is 3 volts. Here,
Clear.
okay, this is about it. You can try to do this as a homework if you want. Find I of 0 plus V of 0, IL of 0 plus VC of 0 plus VR of 0 plus DL by DIL of 0 plus by dt, dVC of 0 plus by dt, dIVR of 0 plus by dt, IL of infinity, VC of infinity, VR of infinity. Okay, this problems because I want you to be clear on concepts. That's why I'm giving you these.
Sir,
Okay, t equal to 0
how
plus
to find dvr 0 plus by dt?
dVR 0 plus by dt.
Yes, sir.
Similar way, just now we did it. How I found the voltage across the resistor at t equal to 0 plus? At t equal to 0 plus, the behavior of L and C elements. At t equal to 0 plus, how will the capacitor act? As a short circuit or the voltage VC of
Volt-
0?
Yes, sir.
Same, this
Yes,
will
sir.
act as a current source of value I of 0. Okay, so replace them with a voltage source and a current source. Then it will become a simple resistive circuit. And then you can find voltage and current anywhere.
Okay. So then by writing KVL and then derivative, taking
Yeah.
derivative, no?
Yes, yes. Okay. It's a derivative one, right? Yeah. Use KVL and find dVR of 0 plus by dt. Okay.
Okay, sir. Okay, sir.
You can try this. If you don't get it, I'll just ping me in WhatsApp. I'll give you the answer. Okay.
Okay, sir.
Next, as I told you, uh, second order circuits can be solved easily, rather easily by using what you call Laplace transforms. Transform the circuit into Laplace equivalent and then find the solution. Because solving second order circuit, a second order differential equation is a bit tougher one. It's easier to use Laplace transform technique. Okay, so simply to given what you call time domain versus t domain versus s domain conversions. Okay. 1 is equal to 1 by s, or 1 by s is 1. E power at is 1 by s minus a, Laplace transform of e power at. N t power n is n factorial by s plus s power n plus 1. Cos at is s by s square plus s square. Sin at is a by s square plus s square. This is important. These two are important. E power at cos bt is s minus a by, or replace in the same equation, replace s by s minus a. Okay. Similarly, here also s by s minus a in this equation, and t power n into e power at and factorial by, again same, the same one, replace s by s minus a. Okay.
Okay.
Yeah. This one more important one. The network shows equivalent of an inductor in Laplace domain. Determine the initial current through it. Rather, let me okay. Let me transform the equations or capacitors and inductors. So this is my inductor. Laplace transform of an inductor will be something like this. See, you have to write it in the form of V is equal to IR. Okay, remember this. So what is the voltage equation? This is I. So V is equal to L di by dt. Laplace transform will become V of S is equal to L into S, or SLI. Okay, I can write S into Li. Okay, so what happens? This L is becoming SL. This is how it will become SL in time, what you call frequency domain, or sorry, Laplace S domain. Okay. This is valid when initial conditions are 0 or the inductor is uncharged. Okay. So if the inductor is charged, what happens? I'll get one more what you call current value. So this will become SLI or something like this. As I told you, at t equal to 0 plus, what happens? Inductor will be replaced by a short circuit and a current source in the same direction. Okay, but this is a generalized equation. So this will be L and this is I naught. This will be SL and I naught. Okay, SL and I naught. This is how you transform an inductive circuit. Okay. Similarly, for capacitance, plus minus P, C, I is equal to C dV by dt. So this will become I of S is equal to SC into V of S, or V of S is equal to 1 by SC into I of S. Okay. C will become, capacitance will become 1 by SC. I think I have done some mistake. Let me see. Okay, 1 by SC, this is correct, but this current source is wrong. You won't get a series current source, it will be a parallel one. Why? Because at t equal to 0 plus, what happens to an inductor? It won't get short circuited, it gets open circuit. Open circuit, no current flows. That is why it should be in parallel. Okay, sorry for this. The current source should be in parallel to the inductor. Why? Because at t equal to 0 plus, the inductor acts as an open circuit, not a short circuit. Okay, t equal to 0 plus, inductor acts as a open circuit. So if for the current to flow, this should be the case. It should be in parallel. So for in a capacitor, it will be something like this. It is a voltage source of value V naught. This is 1 by SC. Again, at t equal to 0 plus, the capacitor acts as a short circuit, but you'll have a voltage V naught across it. Okay.
Okay.
This is I naught. Okay. So what is okay? If this is I naught, this will be I naught by S. This is V naught. This is V naught by S. Okay. Okay. Laplace transform of 1 is 1 by S. So Laplace transform of constant I naught is I naught by S. Laplace transform of constant V naught is V naught by S. So this is how you transform L and C elements. So what about resistance? It's V is equal to IR. Same. It won't get changed in case of Laplace domain. Same. Okay, resistor won't get changed from T domain to S domain. Okay. This is about capacitor. This is about inductor. Remember, inductor will have a parallel current source. Capacitor will have a series voltage source. Okay. In case of resistor, there is no change. T domain to S domain. Clear?
Yes.
So the network shows equivalent of an inductor in Laplace domain. Determine the initial current through it. Okay, this is an Laplace domain equivalent. Find the initial current. What is initial current through the inductor? I naught. Find I naught through this. See, Laplace domain of an inductor is something like this. As I told you, this is my Laplace domain. What is the value of this? This is SL and this is I naught by S. Okay, but you have a voltage source in series with an impedance. Here, current source in parallel with an impedance. So I can transform this. Sorry. Okay, I can transform this using source transformation technique. This can be transformed to a voltage source in series with an impedance. Okay, what will be the value of this voltage source? Will be equal to I naught by S into SL. S and S gets cancelled. I naught into L. And this will be same as S into L. So here it is given I naught into L is equal to 6 volts and L is given, or S into L is given as S by 2. From this L is equal to 1 by 2. I naught by 2 is equal to 6. So I naught is 12 amperes. I naught is 12 amperes. Okay, clear? It's a 1 mark question. Okay, the network shows equivalent of an inductor in Laplace domain. Determine the initial current through it.
So
Hmm.
here, if we take directly, if we do the circuit like a 6 volt in series with S by 2, so the current V by S by 2, I mean 6 by S by 2 is 12 by S. 12 by S, if we take the inverse, it will be 12, right, sir?
I didn't understand. Why? How can you find a current through this? Because the network shows an equivalent of an inductor in Laplace domain. Determine the initial current through it. Understood the question? You need to find I naught.
I was just telling that by seeing this given circuit, this 6 volt in series with S by 2,
Hmm.
in the Laplace domain itself, if we take the current like I equal to V by like 6V by S by 2.
That's what I did actually. That's what I
Okay.
did by converting this.
Okay.
That's what I did by converting this. Okay.
Okay.
I just had to show you this way because the concept here is it's a Laplace domain of the inductor, but it is taken in this form, voltage and an impedance form, rather than the usual form is this inductor in parallel with a current source. But here inductance in series with a voltage source. This is what it has been given. Okay, and if you can see, there is no S term here. But in case of an inductor, the current source will have an S term, right? In case of capacitor, the voltage will have again 6s. Okay,
Okay.
so
Yeah, okay.
those things are important. That's why I have this here. If you can see, the S gets cancelled. That's why you're getting V as a constant value. Okay, that is why you're getting V as constant value.
Okay.
The S term is getting deleted or cancelled. Okay, I just want to give you the concept of this. This is a second order circuit. If you, oh, sorry, I'm sorry. This is a first order circuit. We are talking about the second order circuit. Sorry. So again, these are all important questions. Previous year gate questions and all. But as you can see, these are all of 2 marks each. You'll get once in a while. Second order questions you won't be getting usually in gate. Okay. So try to do this in the circuit shown in figure. The switch S is closed at t equal to 0. The voltage across the inductance at t equal to 0 plus is dash. Voltage across the inductance at t equal to 0 plus the switch is closed at t is equal to 0. Can you tell me the voltage across the inductance? Quickly. So at t equal to 0 plus, what happens to the inductor? What happens to the inductor just after the switch is closed?
It's a 4 volt.
Open circuit.
Yes, 4 volts. Okay, at t equal to 0 plus, you have to draw the circuit. At t is equal to 0 plus, what happens? Initially, the capacitor and inductor are not charged. T equal to 0 plus, my inductor acts as a short circuit. Sorry, capacitor acts as a short circuit and inductor as an open circuit. So this is how the circuit is. 4, 4, 3, and 10 volts. Okay, so if you know the concept, the answer is, I think, as you said, it's directly you get the answer. VL of 0 plus voltage across the inductor. So these two are in parallel, 2 and 3 series, right? 10 volts gets divided, 6 and 4 volts, right? So this is 4 volts. Option B. Okay, it's a 2-mark question in GATE. 2 marks you can directly tell by seeing only if you know the concept. So t equal to 0 plus how the capacitor and how the inductor behaves. Okay, this is
Once again.
what you need to know. Okay,
Okay.
what happened?
Sir, how it became 4 volts, sir?
Okay, so what is the circuit here? Plus minus 10 volts,
I just missed something, I think.
3 and 2. Okay, this is the voltage. So use voltage division rule. 10 into 2 by 5. 5 2 is 10, 2 into 2, 4 volts.
Okay. I missed. I think I have written something else, like thought something else instead of 2. I got 6 and I thought something else.
Okay, is it clear now?
Clear.
Okay. See, usually I go with the students, but if you are able to cope up with me, I'll go fastly. I'll directly write answers. If you want, I can give you the explanations. Okay, this is as simple because 2 marks. I just want to show you by looking at the question, you can directly answer without putting pen and paper or pen on the paper. You can directly answer these type of questions. Okay, that's what I want to show. Okay, yeah, the same. Sorry. Determine V and I for t greater than 0. Determine V and I for t greater than 0. I don't want you to solve it completely, but I just want to give you the basics for doing this. Okay. Okay. because solving a second order circuit takes time, but I'll show you how to solve this. Okay. So at t equal to 0 minus, what is the circuit? The switch is open. So initially, inductor and capacitor not charged. Okay. Initially, the capacitor and inductor are not charged. Now, I want to convert this into a Laplace domain circuit. So for doing this, you don't have to calculate any what you call V of zeros and V of infinities or nothing. You need to calculate V of zeros and I of zeros. No need to find out the time constants and all. Okay. Rather, you can find the time constant and you can verify it if you want. Okay.
Yeah.
See, this is the circuit. So I want to convert this into S domain. Okay. So I'll write the circuit. Everything will be impedances 10. So capacitance will be replaced by 1 by SC. So 20 by S, right?
Right.
And the current source 3 amps. You're saying something?
Nothing.
Yeah, 1 by SSC is 20 by S. Current source will be replaced by 3 by S. Okay, and this switch is closed. And this is 4. And inductor will be S into L or 2S. Okay, This is how it is. Okay. For example, now I need to find what you call the voltage V here. V is given as here. So let me call it as VA. Okay, I can use something called as nodal analysis. I can use a mesh analysis. It's a super mesh equation. Okay, use all the techniques you have in your what you call DC network. Simple as that. Or you can you can use what you call the current division rule. I want the current here. I is equal to the total current. Okay, total current is 3 by S. Current division rule I'm using 3 by S into 3 by S multiplied the total current multiplied by the opposite impedance 10 plus 20 by S divided by the total impedance 10 plus 20 by S plus 4 plus 2S. Okay, so this is how you actually do what you call using Laplace S 10S plus 20 divided by yes. You need to know 14. Okay, 14s plus 2s square plus 20. So s and s gets cancelled. So this is how you'll get it. You need to again what you call factorize this, and you have to apply inverse Laplace transform to get it. Okay, the important point I want to tell you is how to write the given circuit in terms of S domain. After that, it's simple. You can use all the network analysis techniques you learned so far. You can use nodal analysis, mesh analysis, current division rule, voltage division rule, whatever you want, you can use those. Okay, so this is how you have to do it. Okay, using Laplace transforms.
Okay, okay.
Sir, in this
Okay.
circuit,
Hmm.
one time constant is left on RNC and another one is L by R for the right hand circuit. Right hand part.
Okay. Yeah, actually, time constant. It's you'll definitely get two time constant. And if you have seen this, R equivalent C is one time constant, and L equivalent by R is the other time constant. But it's better to do this way. You'll get the proper time constant in this way. If you do this, you'll get after doing the inverse of this, you'll have both. Okay. Sometimes there will be two decays. This will be something like this. The current will be again raised to someone. So this will have a different time constant tau 1, and this will have a different time constant tau 2. Okay. So this can happen this way. That is why I want you to do this way. Okay.
I think in this method also, because by factorizing the denominator we get two S terms, right? So in the time domain, we will get two.
Yes,
Uh,
time constants.
okay, okay.
Yeah. Two exponential terms. Two time
Exponential, exactly.
constants.
Okay, okay.
Okay, sir.
Okay. With the sources, sometimes you'll get, see, this is also possible without source, I mean. Okay. Exponentially decaying sinusoid or exponentially rising sinusoid. Okay. Exponentially rising sinusoid or decaying sinusoid with an offset, sometimes with an offset. Okay. These are what you get in case of RLC circuits. Okay, and this is an RLC circuit. Okay, you'll get something like this e power at or e power minus at sin bt or e power at cos bt. Okay, exponential decaying or exponentially rising ones. Okay, all these are possible. But as I told you, in second order circuits is not there in the syllabus, at least not for gate. And similarly for HAL also, HAL they have directly mentioned the syllabus will be similar to that of GATE. In the last 12 years, if you see, there is no second order direct question in GATE. Okay, that's something like this, as we have done something like this at t equal to 0 plus, just to test your concept, whether you know what happens at t equal to 0 plus. And this one, whether you will get what you call this one is a GATE question actually. Okay, important. And what else? Yeah, these ones. D square I of dt square. Okay, di by dt, d square I by dt square. Because they want to test you, you know the current is zero, but will the rate of change of current is zero or not? You should understand why it is not zero. Okay, so they'll test your concepts rather than your mathematics in networks at least, because mathematical solutions takes time, and now the calculator is not allowed in gate and all. So this is not important as such in second order circuits, but you should know how to solve this. Okay, in your regular exams, it will be very helpful. Okay.
Okay.
Sir,
Mm-hmm.
sir, in HL means our gate syllabus is more than sufficient, no?
Yes, HL, if you see the notification, they have written the syllabus is same as GATE, because they haven't mentioned any separate syllabus. And GATE syllabus is very wide. It is sufficient. Okay, it's sufficient for any competitive exam rather. Okay.
Okay. That means in mathematics also,
No, I'm not getting your voice clearly. What were you saying?
mathematics is also for HL exam, no?
Yeah. Mathematics is also there in GATE, but
Yes, sir.
in case of what you call HAL, I don't think you'll directly get something in mathematics, because in HAL is directly MCQs, no fill in the blanks, nothing, and only 1 mark questions directly. Okay, so only theory-based questions. Mathematics, I hardly think you'll directly get any questions that way. Okay, you need to solve mathematics, right? I don't think you'll get it from, but obviously using concepts of mathematics in networks, signals, EMT and all, those type of things you'll get. Case of missions, power systems, you'll definitely use mathematics. In power electronics, rather, you'll use mathematics, right? You'll use what you call the variable separable methods, and what you call inverse Laplace transforms in and all this complex conjugate numbers in what you call AC circuits. All these concepts, obviously basics of mathematics, are important. Okay.
So in HAL,
You'll also have aptitude HL.
the second order circuits,
Okay, sir.
what can we expect maximum actually in
Uh,
HAL?
HL, as I told you, the concepts like these one, okay, you should understand what happens just after the switch is closed, before the switch is closed, rather than solving for V1 and V2 for t equal to 0. T greater than 0, you'll get an equation in terms of E of AT sin BT or E of minus AT cos BT, something like this, right? So instead of solving for the entire equation, they just want you to know what happens at just after the switch is closed. T equal to 0 plus condition and t equal to infinite condition. These are very important. T equal to 0 plus is a transient, t equal to infinity is the steady state condition. Okay.
Okay, okay.
Yeah. So transients, most likely first order circuits, those four equations are given you, those four. And in case of second order circuits, all these concepts are important. Okay. Just after the switch is closed, because people simply remember this way: capacitor acts as an open circuit for DC, but at t equal to 0 plus instant, it acts as a short circuit, or it will be replaced by a voltage source and a short circuit, right? Similarly, inductor acts as a short circuit for DC, but it acts as an open circuit at t equal to 0 plus. Those points or those instants are important. Okay.
Okay.
Okay. I'll start something called as triple SA. Let me stop sharing.